So here you go. Let's quickly review what we did last time for electricity, right? The important thing is electric charges. That's a new quantity. It's like I can say it's a new idea. It's a new beast, right? It's a new property of matter, which is different from mass. There are positive and negative charges. Positive and negative charges attract themselves. Positive and positive repel. Negative, negative repel. Repel the charges. And we have electric force, just like we have for the gravitational force. The formula for the electric force is similar to the formula of the gravitational force. We have this phenomenon of electric polarization. And we have this idea of the electric field. It's like an invisible quantity that we cannot see with the eye, but we can measure with equipment, with instruments. Related to the idea of the electric field, there is this idea of electric potential. It's a little bit more difficult to understand the electric potential. It's a little bit more difficult. So let's talk about that. And if you want to understand better this thing too, you can take a look at some simulations. Electricity and magnetism is kind of difficult. Okay, it's not easy to understand because it deals with the invisible world. Electric charges are invisible to us. We can see an electric force, okay, but we cannot see electric charge. And when it comes to the electric potential has to do with energy, just like we have gravitational potential. So let's go back here. The idea of electric potential. Electric potential. Okay, if you want to understand electric potential, you have to understand, go back to what we covered before, potential energy. Potential energy, okay? So what do we have? We have electric potential energy, okay? And we also have electric potential. So the potential energy that we studied before, okay, is in reality, the gravitational potential energy, to be more explicit. Okay? Remember, when we are doing energy, we are raising an object against the force of gravity. We're raising upwards. And what we are doing, the moment that we are raising this object against the force of gravity, we were pumping potential energy into this object. You have to picture that in your mind. And this type of energy is something that you can use to do some useful task. Okay? If you're smart enough, the moment that you raise an object against the force of gravity, now if you're smart enough, you can figure out a way to tap into the potential energy that was pumped into this object. But this potential energy is due to the gravitational field, this potential energy of the gravitational field. Okay? So you have to understand the gravitational potential energy before you understand the electric potential energy and the electric potential. Okay? One example of a device that stores electric potential energy, let me get it. Here you go. Is your regular battery. Here you go. This little thing here has some energy stored inside it. And the type of energy that it has is electric potential energy. Okay? And then related to the electric potential energy, there is again what we call the electric potential. Let me get another battery here. There you go. I have another battery here. I Have you ever seen this other battery here? Two different batteries. This little AAA battery, or AAA cell, we call it, and this square one here. And then we have another battery in our cars, okay, which is bigger than those two. So what's the difference between those batteries? They, deep inside, down deep inside, they're exactly the same device. Down deep inside. They all store electric potential energy. It's just how much electric potential energy they store. This guy here, is a cell that has an electric potential of 1.5 volts. Have you ever heard about the voltage of a battery? That's what this cell does. Between the terminals of this battery, you have an electric potential of 1.5 volts. Then I'm going to explain more what this voltage is all about. This one that you see here is 9 volts. It's written here 9 volts. And the one that we have in our car is 12 volts. Okay? So the unit for the electric potential is volts. And I'm going to show you what that means. Okay, but just remember that potential energy, what's the unit of potential energy? Any energy has a unit of joules, right? Whether it is a gravitational potential energy or if it is electric potential energy. The unit is in joules. But how do we get energy how do we get electric potential energy? Electric potential energy, gravitational potential energy, okay? So in order to pump gravitational potential energy into a device, into an object, we have to raise it against the gravitational field, okay? Now, in order to pump electric potential energy into a device, we do something quite similar. Okay? Just for instance, just think about getting two electric charges. Okay, one positive and the other negative. Okay, let's say I'm holding two electric charges, one positive and another negative. Those two electric charges, they tend to attract themselves, right? That's what they tend to do. They want to come together. But if I prevent them from coming together, like holding them in place, they are going to store energy inside themselves. Just like when I raise this object, my cell phone, for instance, against the gravitational field, this object wants to go back to the position where it was. The moment that I raise it, what did I do? I pumped potential energy into this object. Here is similar, okay? So let's say this guy is right in here. We have the positive and positive charge and a negative charge. They are together. Their electrical potential energy is 0. But the moment I start to raise this electric charge, move this electric charge away from the other one, what am I going to do? I'm going to start storing electric potential energy into those two charges. When I release this charge, this charge is going to automatically move towards the other, and the electric potential energy that it's going to convert into kinetic energy. Okay? That's the idea that you have to have about electric potential energy. It's kind of similar. So again, gravitational potential energy, you raise a mass against the gravitational field. Okay, and when you do that, you pump energy into this object. Okay, so how to pump gravitational potential energy into an object, okay? Well, you have to raise it against the force of gravity. That's what you have to do. When you do that, you add, you add gravitational potential energy. So before there in that chapter of energy, we just called it potential energy. We didn't call it gravitational potential energy. Now I'm calling gravitational potential energy to distinguish from this other potential energy that we call electrical potential energy. Okay? So what about electric potential energy? How to pump electric potential energy into a system. Not into an object, but into a system, okay? That would be a better. Into a system. The system in this case is the mass plus the earth. That's what we're doing. We're separating the earth from, we're separating my cell phone from the earth. Okay? Mass plus earth. How to pump electric potential energy into a system. In this case, the system is going to be, let's say, for instance, e.g., one positive charge and another, a positive and a negative charge. Positive and negative. One positive charge and a negative charge. So again, we have one positive charge and one negative charge. They are initially, stuck together because they attract each other. So if I want to store electric potential energy in a system, I have to separate those two charges somehow. I can do this with my hand or I can do it something else. If I hold those two charges apart like that, I will have stored electric potential energy into this system. Okay? Did you get the idea? So here you go. How to pump? You have to separate. Let's see. How to pump electric potential energy into a system? Okay. You have to separate. Here you go. Two electric charges of different signs. Okay? Positive and negative. If you separate them, you pump potential energy, positive and negative. When you do that, you add. When you do that, just like in the gravitational potential energy, okay, you add electrical potential energy. And that's exactly what we do in those batteries. If you are very careful about what is written here in the battery, I'm going to show that to you. You have two terminals here, okay? In this battery, you have two terminals, one here and another here. And in this battery, you have also two terminals. One terminal here is at the bottom of the cell. The other terminal here is at the tip of the cell. Okay? Those terminals, they are labeled, by the way. Take a look here at my 9-volt battery, at my 9-volt cell. My 9-volt cell, one of the tips is labeled with the positive sign. Okay? So this tip that you see here, in this tip that you have here, you have a concentration of positive charges. In this other tip that you have here, you have a concentration of negative charges. Those charges are trying to get together. They are attracting one another. But the battery was built in such a way to keep them apart. Keeping them apart ensures that you have electrical potential energy stored in the system. Okay? And what keeps them apart is actually a chemical factory that we have here inside. We have some chemical paste here inside that ensures that the negative and positive charges are separated from one another. Okay? So that's the idea of electrical potential energy. In order for you to understand electrical potential energy, you have to understand the other potential energy that we discussed before, the gravitational potential energy. So here we go. In the case of a battery, we have an amount of positive electric charge separated from a same amount of negative electric charge. Okay. What allows that to happen? What ensures that something like that happens is the chemicals inside the cell of the battery. And by the way, we can build a battery very easily. It's not difficult to build a battery. So let me give you make an illustration of that. P300. Let me use those drawings here. Okay, so here you go. I'm gonna draw a 9-volt battery here for you. It looks just like that, right? A 9-volt battery is like a square block like that. A tip here at one end, a little bit shorter than that. It will be the male connector of the battery, and another tip a little bit larger and make it smaller. Okay, like that. This is the negative, this one is the positive. This terminal here the one on the right side is the positive terminal, full of with a bunch of positive electric charges. And on the other side, we have the negative terminal with a bunch of negative charges. Nine-volt cell. This is the 9-volt cell. It has potential energy because those electric charges are separated. In the case of the 1.5-volt cell, the situation is similar. Here you go. It's just the geometry that's different. It's a cylindrical cell, almost the same size. See that? Almost the same size. The positive terminal is a tip, just like this one, or like that, smaller, thinner, and it's shorter as well. Okay, that's positive. And the negative is there at the bottom. This cell is not at 9 volts. This cell is 1.5 volts. 1.5 volt cell, approximately. Put it like that. Here you go. Negative and positive. The charges are separated, and the chemical here inside this cell ensures that those electric charges remain separate. It has a potential energy. Did you get the idea? Those two charges are trying to come together, but the chemicals here in the cell doesn't allow it to the charges to come together. That's how you have. That's the picture that you must have for this type of situation. And you have the battery of your car too. Okay, it's something much larger than those two cells, by the way. Nothing. I'm not making it. Not putting that in scale. Okay. So it's two tips, right? One is positive, the other one is negative. What a battery is just a device that has a separation of charges. By separating the negative from the positive charges, we manage to create an electric potential energy there. We happen to store an electrical potential energy. So here we go. So by separating one positive electric, by separating positive, not one, but positive electric charges from negative electric charges, we create we pump, not create, let's say, we pump, we manage to store, here you go, manage to store electric potential energy in a device like a battery. Battery is not the only one that can store energy, electric potential energy. Okay, there is another device called the capacitor, but battery is the most familiar one that you are with, like a battery. There are other devices. There are other devices capable of storing electrical energy, such as the capacitor, which is a device far simpler than the battery, which is far simpler, a device far simpler than the battery. And they sell out there. They sell those things out there. We can store electrical potential energy in a device such as a battery. Okay, so here you go. So let's go ahead and rewrite what we did before, right? Electric charges. You gotta believe that there's something like that called electric. There is a property like that for the matter. There is electric force, and there is electric field. Okay, is the ability. What is electric field? Is the ability of exerting an electric force in a given point of space. That's how I like to define electric field. And what else did I tell you that? Next one is just electric field. Yeah, okay. I can put electric polarization. I'm gonna put electric polarization in the right place. Okay, electric polarization is supposed to be here in the place of force. Here you go. Electric polarization comes before electric force. Let me correct there upstairs. Good. And after the electric field, we have electric potential energy. I should have put that before. Okay. So, and after electric potential energy, we have this concept of electric potential. And then we have sources of electric potential energy. Electric potential is slash electric potential energy. Potential energy. Electric field. Now the next step is electric potential energy, which is joules. The unit is the joules. And after electric potential energy, we have electric potential. And how is the electric potential related to the electric potential energy? There is a neat relationship in there. Okay? What is the electric potential? Well, electric potential is electric potential energy divided by amount of charge. That's exactly in your book. Let's put that here. It's just a convenient way of talking about, I'm going to put like that, EPE for, this guy called electric potential, we call it V, okay? Electric potential energy, we usually call EPE. So electric potential, V, is just a convenient way of talking about the electric potential energy by amount of charge. And the unit of electric potential is the joules divided by coulomb. Right? So here you go. Electric charge can be measured in terms of coulomb. Oh, here you go. Electric polarization, we don't talk about that. Electric force, we measure. There's no such a thing as a unit for electric polarization, okay? Electric field, the book doesn't say, but I can tell you that electric field is Newton per coulomb. Electric potential energy is joules. And the electric potential is joules per coulomb, which shows up so frequently in physics that we call it the volts, abbreviated by the letter V. Okay? So 1 volt is what? 1 volt is 1 joule per coulomb. 1 joule per coulomb. So we say that a 1.5 volts, a 1.5 volt battery gives 1.5 joules of energy for every 1 coulomb of electric charge. a 12-volt battery. Let's talk about 9-volt battery. That's the one I showed to you, right? Gives, provides, not gives, but provides, right? Provides 9 joules of energy for every coulomb of electric charge. A 12-volt battery provides 12 joules of energy for every coulomb of charge, and so on. That's what electric potential is all about. Voltage sources. I told you, voltage sources. Batteries are voltage source. Are sources of voltage. Batteries. It's very simple, very easy to build a battery. Very simple. And we do that in the lab, in the P300 lab. When, of course, doing the regular lab, right? I'm going to show you a way to build a battery. I'm going to get some of my raw material. I'm going to show you. Hang in there. It doesn't require fancy materials to build a battery. Okay? Back the moment that man invented different types of metals, they were able to invent a battery. They were able to build a battery because everything else is readily available in nature. I have here with me an orange. Okay? I can make a battery out of this orange. Okay? Just by combining this orange with two different metals, you can even get a nail, for instance, of iron and a nail of copper. You insert that into your orange. It doesn't have to be an orange. It can be any fruit, a lemon, an orange, a watermelon, and you make a battery out of that. Okay? It's very easy to build a battery. It's not going to be a very reliable battery, but we find out that we can store electric potential energy in something like that. So this guy and this guy, they work much alike. All I need to do here is to insert two different metals into my orange. Okay? One way to build a battery, one way to build a very simple battery is by using a fruit. Don't forget that the juice of the fruit is an electrolyte. Okay? By combining a fruit with two different metals, such as iron and copper. But like I said, it doesn't have to be an orange. It doesn't have to be a fruit. It can be even salt water. Does that too. You can have a salt water a container with salt water. You can put, a nail of iron and another nail of copper in the salt water, and you create a separation of charges. You do create a separation of charges. Okay? So just imagine, I'm not gonna spoil my orange here, but suppose that this was a nail of iron. I would stick it here inside, and the other was a nail of copper. I would stick it inside. What happens? One nail becomes positively charged, the other becomes negatively charged. Which one becomes positive or negative depends on the on the characteristics of the metal between one another. If I put iron here and iron here, you don't get a battery. You have to have different metals. You have to use different metals to create a battery with this simple material. So here you go. Salt water. You can also use salt water. You can also use salt water as an electrolyte. Okay. But you must. The metals cannot touch one another. Okay. They have to be separated there in the juice, of the fruit. But you must have two different metals to pump electrical potential energy into your system. Okay? So here you go. Let me draw another battery here for you. I'm gonna take advantage of this one here. No, I don't need that. Here you go. What I'm gonna do like that. My orange. Those oranges, those fruits, they usually produce like 1.5 volts. Okay, here you go, my orange, and I'm going to stick, for instance, here you go, a nail of one metal. Here you go. Copper is usually what, this color, right? Nail of one metal and a nail of another metal. I just changed their color, so like that. One is going to become positively charged. Just by doing that, one becomes positively charged, the other becomes negatively charged. And it has all to do, as everything related to the chemical energy that you have in the juice of the fruit. Okay? Fruit and two different metals. That's one way. There are several ways. But you cannot, like I said, you can also have a container, a salt container. I'm gonna get this one here. Container with salt water. Container with salt water, for instance. Yeah, and it doesn't have to be salt water. It can be even your Gatorade that has an electrolyte there, right? Container with salt water. Salt water and two different metals. Here you go. I'm gonna get those two metals here. Battery again. They cannot touch one another. And when you do that, one terminal becomes, we call it electrode. The terminals we call the electrodes, right? The terminal is this part, but the nail itself is the electrode. Here you go. One is going to become positively charged, depending on the metal, of course. Okay. And the other is going to be negatively charged. Okay. So that's what we have for the voltage sources. It causes a potential difference. So this guy here is like a pump of electric charges. That's what a battery is. That's a very good analogy. A very good analogy for a battery. A very good analogy of a battery and a mechanical device. Let me see. A battery is the electrical counterpart, here you go, of a mechanical pump. Mechanical pump. A battery pumps electric charges in a circuit. Okay? 555. And because we have electric potential energy stored here in this device, I can, for instance, light up a light bulb. I can do that. Okay? I have some LEDs here with me. Let me show you. And I'm going to light up this LED with this battery. LEDs. I have a bunch of LEDs here. Green LED. But I gotta be careful. I gotta be careful not to burn out my LED, okay? I cannot let it stay there in the terminal of the battery for too long, otherwise I'm gonna burn out my LED. It's amazing. 30 years ago, we didn't have something like that, okay? 30 years ago, something like that didn't exist in the market. 30, 40 years ago. Not as cheap as we have today. Those little devices, they cost peanuts. You can buy one of those by 1 cent, as low as 1 cent. Oops. But if you're buying just one or another, you pay them 10 cents, okay? So here you go. Let's see if I can get it. Light up. No, not this way. Yeah. Take a look. I gotta be careful, okay? I cannot hold it for too long there, otherwise it's gonna burn out. Do you see here? So electrical energy stored here managed to light up my LED. And if I keep it here for too long, it's gonna burn out. Okay? What we have here is a circuit. So this LED is using up electric potential energy of this cell. So a battery, the energy of the battery, the electric potential energy of a battery can be used to light up an LED. As long as we have electric potential energy in the battery, in a battery, it is possible to light up the LED. $5.58. Let's see, let me take attendance. July 1st. Blaze, are you there, Blaze?
Oh, sorry, I'm here.
Okay, good, thank you.
I'm
Kyla
here.
Bogdanov, are you there?
Here.
Okay, Courtney.
Here.
Okay, Christian Seron.
Here.
Next, Madeline, are you there, Madeline? I think Madeline is here, right? No, she's not here. Okay. Cynthia? Cynthia is here.
Here. I'm here.
Okay. Raquel, Cornelius. Just tell me that you're there, Raquel. Okay. Brittany Ewing.
Here.
Okay. Melissa Flores.
Here.
Taylor Givens.
Here.
Evelyn Gomez.
Here.
Brittany Gonzalez.
Here.
Jessica Gonzalez.
Here.
Jacqueline Johnson. Okay, having computer issues. Okay. Okay. Let me. Okay. Okay. So Jacqueline is here. Okay. Let me send a message to Jacqueline. I'm gonna send you a message to chat. Okay, Jacqueline. Okay. 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 Good. Thank you, Raquel. Cornelius. Yes. Okay. Rhonda, are you there, Rhonda?
Here.
Next, Paloma.
Here.
Allison. Is Allison there?
Yeah. Yeah.
Okay. Good. Thank you. Yareli.
Here.
Okay. And Brian Silvestri. Are you there, Brian? Okay, I'm gonna put no answer, okay, Brian, whenever you answer. Okay. Okay, so that's where the idea of electric current comes from. Okay? Once I connect my LED here to this battery, the electric potential energy is used to make the electric charge move in this LED or in a circuit. And that, remember what I told you about electric current, right? Electric current, what's electric current? Electric current is the motion of electric charges. By the same token, we have water current, which is the motion of water, which is the movement of water, which is water in movement, right? Water in movement, comma, electric current is charge in motion. So let's continue with our evolution of concepts here. Here you go. So I can put electric current right in here at this level. Okay. You don't need the concept of electric potential to understand the concept of electric current. Charges that move. Electric charges that move. But in order to get an electric charge to move, you need electric potential energy. So let's go ahead and let's have our break now. It's 6:05. Any questions? Okay, to 6:20. And then around 7:30, we have our exam. Okay. So I see you in 50 minutes.
Oh,
Yeah.
Professor.
Yeah, go ahead.
So let's say if I turned in my homework 7 and 8 on Tuesday, will it both be graded by Thursday?
Let's see here. 7 and 8. Well, I grade everybody at once. Okay, I can only grade everybody at once. I cannot grade half one day, half another day. If everybody turns homework 8 on Tuesday, yes, I can do it. But I already gave you until Thursday to turn in homework 8.
And is there going to be a homework 9?
No, there won't be a homework 9. We are not gonna
Oh,
cover
okay.
magnetism. We're gonna cover just. We're gonna finish. We're gonna stop here on chapter 8. Okay.
Okay.
We're gonna stop here in chapter 8. Okay. So let's go for our break. I see you in 15 minutes. let's go back. Okay, so let's go back to our electric current. So electric current is just like I said, is the motion of charges. And how do we quantify electric current? Okay, you gotta visualize. I'm gonna illustrate here how you should visualize an electric current. Okay, just get your regular wire, copper wire that we have out there. Let me get mine here. Okay, here's my copper wire. It is insulated. Okay, you have a metal here inside. So just picture, my metal wire, my copper wire right here in my screen, my computer screen. And the electric charges can be pictured by circles. Oh, here you go. Circles, circles. Inside, very important piece of information that you have to have. Inside a copper wire, a metal wire, not just a copper wire, but a metal wire, the only charges that can move are the electrons. Okay, so I'm going to write that down here. Inside a metal wire, such as a copper cable, such as a copper cable, the only charges that can move and produce a current are the electrons. So going back here, we are going let's move. God, here you go, I got them. More. And then I gotta get the negative charges, the symbol of the negative charges that are inside. Uh-oh, beam up. Format shape. Here you go. Oops. Oh gosh. I get it. Here you go. I got it. The positive charges don't move at all. Okay, so let's write that down here in my notes. Charges positive charges do not move at all. They stay still. They stay still. Okay, but don't forget, just in metals, just in metal wires. So what I'm going to illustrate how a electric current looks like. Okay, if you could see those electric charges there, inside the wire. An electric current would be something in which those electric charges are moving from one place to another. Oh. We go. Here we go. We can. That's the arrow indicating the motion of this charge, the direction of motion of the charges. Okay. Now, if you were able, so here you go. Here's the cross section of my wire. Is a cylindrical wire. Okay, the cross section of my wire area. If you are able to count how many of those charges cross this point right here, you would be able to determine the current in your circuit. Okay, how many charges cross this point right here, just like a gate. Picture that just like a gate. You know, have someone counting how many electric charges goes through this region. 1, 2, 3, 4, 5. Okay. So the definition of electric current current. The symbol for the electric current is the I, number of electrons divided by amount of time. Number, oh, let's see, number of charge, let's see. No, amount, not number of charge, not number of electrons, amount of charge. Okay? Current. I is the symbol for the current. Amount of charge divided by amount of time. So if you count a given number of electrons, okay, number of electrons, right, N times the electric charge of the electron divided by the amount of time. I'm going to put that in a symbol of delta T. Okay, that's what we get for the current. You go ahead, count the number of electrons that pass through here, the number of the electrons times the charge of the electron that you already know in coulombs, divided by the amount of time, and you get the current. That's how electric current is defined mathematically. The unit of electric current then is going to be what? Here you go. Square bracket means unit. is going to be the unit of charge divided by the unit of time. The unit of charge is the coulomb. The unit of time is the second. Coulombs per second. It's like, you can think of that as some sort of charge speed, right? The speed of the electric charge. This unit shows up so constant, so frequently in physics, that we call the ampere, and abbreviated by, or amps, right? By the letter A, ampere or amps. That's the unit of current. Common values that you find out there for the electric current, is on the order of, let's say 5 to 30 milliamps, which is, 0.005 amps to 0.030 amps. That's the common values of current that we find out there. And it's possible to measure those things with a device that we call the ammeter. We can measure a current, current values with an ammeter. And those devices are very cheap. Similarly, voltage we measure with a voltmeter. How do we get the electrons to move in a circuit? That's the next question. Okay, that's the next question. Let's see, electric current. Well, we do the following. We connect this wire that you see right in here to a battery, like that. Okay, I'm not gonna do that because I believe I'm gonna provoke. Here you go. Yeah, that's okay. I may burn out my wire, Let me see what's gonna happen. Yeah, I'm not gonna take this chance. I can even damage my battery because this wire here has a very little resistance, so you can end up not only damage a wire but damaging your battery. Okay, so here you go. To get those electrons moving, what you have to do? You have to come up with an electric charge distribution at this end of the wire. Here you go. That's positive. That's what you have to do. If you somehow manage to distribute positive electric charges right in here, you will attract those electrons and you're going to produce a current. Okay, similarly, if you put a negative charge distribution right in here, you are going to repel those electrons towards the other end of the wire. Okay? So that's so how do you do that? Okay, you do that by connecting this end of the wire. Here you go. Let's go to the next step here. Next step. We do that by connecting this end of the wire to the negative side of the battery. To the negative side of a battery. Here you go. The battery, I'm going to get my wire here. Here you go. Connecting right in here. I'm gonna take out this guy from here. Here you go. Think of that line that you see here, a wire. Ah, boy, this guy is not working, is it? Okay, now it looks like I got it. Ah, you know what? I'm gonna do differently. It's not working this way. I'm gonna do another way. Here you go, like that. The symbol for the battery, by the way, is this, the symbol for my battery is this one right in here. Okay, this end of the battery being the positive side, the other end of the battery being the negative side. So that's how you get to move, to put to create a current in a wire. At this very moment, right here, when I connect my LED to the positive and negative side of my battery, I am producing a current through this wire that makes the LED to light up. Okay, and that's what we call a circuit. The current being the amount of charge going through this cross section of the wire per unit of time. This model you see in the, here you go, in those circuits here in the simulation. Let's see here. I'm gonna come up with a very simple circuit. Here you go. This one, here you go, wire. Okay. I can come up with a very simple circuit. Let me get, oh, here you go, my battery. Battery like that. Get another wire. I'm building a circuit. That's exactly how we do in real life. We get a battery, you get wires, and you can even put a switch. A switch is what we have at the wall to turn on and off the light. Turn on the light on and off. I am going to put another device. Let's put here a light bulb. Yeah, let's put a light bulb right in here. Let's close the circuit. Here you go. Here you go. That's what we have here. Let's see what's the voltage of this battery. Okay, 9 volts, just like my cell. The moment I close, oh, do you see the negative charges here? Those are the negative charges in my circuit. Let's close the circuit. Oh, here you go. I close the circuit. It's not moving. Maybe it's moving very slowly, or maybe I just got the wrong. I guess I got the wrong light bulb here. Let me get something else. Let me get another. Let's try this one here instead. Yeah, this one. Yeah, now we have it. For some reason that other light bulb doesn't work. Okay, so now we have the electric charges moving. See the negative charges moving towards the positive side of the battery. A very good model for you to keep in mind is that those negative charges gets attracted to the positive charges. Remember, positive and negative charges, they stay together, right? And then there is something special going on here inside this battery. It's like a chemical factory that manages to separate the negative from the positive. So the circuit can keep on moving, okay? That's what's happening here. So you have potential energy inside this battery that can separate the positive from the negative charge inside the battery and get the circuit to move, to flow, producing this light. That's a very good model to memorize what happens in a circuit. Voltage source, wires, right? And electric charges moving. You keep on counting. Here you go. So you start counting how many electric charges goes through this region, through this spot right in here. Okay, 1, 2, 3. Okay, let's do that. Let's play a little bit. You know. So those are, suppose that those are electrons. Okay. So I'm going to count how many electrons goes through this hand of mine. Okay, hang in there. So I'm going to start now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 10 electrons in 10 seconds. That's what I counted here. Okay, so it's 1 electron per second. 1 electron times the electric charge of the electron divided by 1 second is the current in the circuit. Okay? That's how you should look at it. On how you can get the current in the circuit. Now, so this type of current that you see here is called direct current. Let's write that down. The current can be measured, right? Current can be measured with an ammeter. And we do have an ammeter there. When electric charges move in a single direction, we have what we call direct current, DC, abbreviated by DC. That's in the book too. If the electric charges move back and forth, the charges move back and forth, then the current is said to be an alternate current. Alternate current, abbreviated by AC. This type of current here, produced by a battery. This type of current here is produced by the outlet in your house. Okay. Back and forth, then you go. Then the current is said to be an alternate current. Let's see if we have a simulation for alternate current. This one is direct current. Here you go. We have a multimeter here, ammeter here. Here you go. This guy can find out what's the current that we have. Right now, he's calculated as being 0.9 amps. That's a very high current. This is a very high current. You don't want to get close to a current like that, okay? I can decrease the value of the current with another device that we call a resistor. We're going to get into that. The voltage, here you go. I can measure the voltage of this battery, 9 volts in this case. So here's the voltmeter, here's my ammeter. a more realistic device is this one that you see here. Not this one. This one is not a realistic device. Forget about this one here. A more realistic device to measure current is this one right in here. You do put the ammeter connected in this. You do put the ammeter in the circuit, okay? If I change the voltage, if I change the energy provided by the battery, if I decrease, let's decrease it. Look what happens to the current. It decreases. 0 voltage, 0 current. No energy, okay? 1 volt, 1/10 of an amp. 2 volts, 2/10 of an amp, and so on. Okay, the charges go faster and faster, and the light becomes brighter and brighter. See that? I'm increasing the voltage, I'm increasing the current as well. Okay, that's a very good way of visualizing this type of phenomenon. So let's see if they have a AC circuit here. Yeah, doesn't. Oh, okay, here you go. No, not this one. No, not this one. Let's see here. Yeah, unfortunately they don't have it. Right, but you know what? I can get a AC circuit going on here. I'm gonna show you. Let me see if I can get. Yeah. I can produce an AC circuit here by moving this magnet back and forth, but unfortunately they don't have an illustration of the electric charges flowing in there. Let's see if they have another one. Yeah, they don't have it, unfortunately. But if you were to visualize again, if you were to visualize uh, an AC current, yeah, right, so go, put the battery here, okay, wires, resistor, here you go. So the way to visualize an AC current is to have the electrons moving back and forth. And how I will do that? I will do that by inverting the voltage in the circuit. Let's close it. Here you go. Right now, it's going in one way, right? But if I were to change the direction of the voltage, oh, here you go. I'm gonna do that. See that? I have an AC current, electrons moving back and forth. This is exactly what you get from the outlet in the wall, moving back and forth. Of course, it's at a much higher frequency. Okay, this type of motion keep on inverting here in real life. This type of motion invert like 60 times per second. They cannot go that fast. Okay, electrons go back and forth like 60 times a second in real life. They keep inverting their direction 60 times per second. That's what AC current is all about. Okay. In real life, electrons move back and forth 60 times per second. This type of current is produced by a device that we call a generator. A generator is a very simple device. Now what's next? Here we go. Let's go back here to our table. Okay. Electric current. Okay, AC current. We have DC current. In one direction. DC current, AC current. As charge move back and forth. Back and forth. This type of current is generated by a battery. Here is generated by a generator powered, let's put it this way, powered by a generator. Powered by a battery. Okay, so here we go. What else can we do here? There is something else called electrical resistance. Electric charge, electric polarization, electric force, electric field, electric potential energy, electric potential, electric current, electric resistance. Let's put all of that in boldface. Here you go. Electric force, electric field, electric potential energy, electric potential, electric current, electric resistance. Electric resistance is the electrical counterpart of friction. That's what you have to know. Friction slows down the motion of an object. So that's electrical resistance. Electrical resistance, that's the same. Okay? Friction, it slows down the motion of objects. And electrical resistance slows down the motion of charges. Okay? What does it do to the current? Brings down the current. That's what it does. So there is an important relationship between the current and the resistance. We're going to see that as the name says, right? Here you go. I'm going to put a proportionality symbol here. Here you go. Here you go, like that. Proportionality symbol. Electrical resistance slows down the motion of charges, consequently brings down the current. There is another, I'm going to get to the whole equation, but right now it's just like that. Let's take a look at the simulation. Here you go. I have my simulation here. I put a resistor here. See that? This is a resistor. I have a bunch of resistors here at home. Every device, every wires, they all have a resistance. But then the resistance of the wires is very, very low. The resistance of this wire that I have here is very low. We can measure resistance with my voltmeter. It's possible to do that with a voltmeter. Now take a look at the motion of those electrons. I'm going to change the resistance of my resistor. By the way, the unit, how do we quantify resistance, right? How do we quantify resistance? We quantify it with the unit of ohms, represented by the capital omega letter. Okay, capital omega, like that. Remember that, ohms. Going back to the simulation, I'm going to increase the resistance and watch what happens. Right now I have only 10 ohms here. Watch what happens to the motion of the electrons. Here you go. I increased. Now the electrons are moving much slower. Okay. Go decrease it. Okay. That right now my resistance is 0 ohms. Okay. Increasing little by little. I can put my ammeter there as well. Here you go. 0.53 amps. Look what happens to the current. Increase the resistance, decrease the current. Okay. Decrease the resistance, increase the current. And what about here, the battery? The battery goes all the way around. You increase the voltage, you increase the current. Decrease the voltage, decrease the current. More energy you give to the electric charge, the faster they go. Okay? So now we can come up with a full equation that relates the current, the resistance, and the voltage in your circuit. The equation is just like that. We call that Ohm's law. V equal to Ri. V equal to Ri. Like that. This relation is called Ohm's law. It's not exactly a law, so I'm going to put that between quotes. Law just in the name. We use this law to build circuits. Here you go. Power source, motion of electrons, resistance to the motion of electrons. That's what we have here. The power source produces motion to electrons. This guy here moderates the motion of the electron. Okay, V, the voltage, quantifies the amount of energy given to the electrons. Okay, the resistance moderates the speed of the electrons. The current quantifies the speed of the electrons. Energy that is given to make them move, right? I think this equation here is far more, this format of the same equation is far more intuitive because the current is directly proportional to the energy imparted to the electrons. The resistance is inversely proportional to the current. I think that's far more intuitive. Okay, 7:15 right now. I can build an electrical circuit here for you. I have resistance. I'm gonna use my battery. I did that to my students. Let me do that quickly. 7:15. I can do that in the next few minutes. Okay, what you see there in the simulation, I'm gonna show you in real life. Okay, I'm gonna use this breadboard to put things together. My LED is gonna go right in here. Okay. Remember I told you it's not a good idea to connect my LED directly to the battery because you can burn out the LED quickly. So then I'm gonna use a resistor to moderate the value of the current. I have my resistors. A bunch of them right in here. There are all sorts of resistors out there in the market. Those devices are mass manufactured, and because of that, they are very cheap. Okay, here you go. Here you go. That's a resistor. Okay. Any device has a resistance. Any device has an electrical resistance. Oh man, here you go. I dropped it. That's okay. My feet has an electrical resistance. My hand has an electrical resistance. My ruler has an electrical resistance. But then there are those, industrially manufactured resistors, like this one, right? That we can use in your projects. I'm gonna connect this resistor to my LED. Okay. So when I put my LED in the same row here as the resistor, it is as though they were connected, physically connected. It is as though they were physically connected. Okay. Oh, here you go. And then there is one more thing that we can do. I don't have a circuit yet because I didn't put my battery here yet, right? I'm gonna put my battery very soon, hang in there. Now what I need, I'm gonna get another device, is a connector for the battery. Yeah, battery plugs. No, that's not the one. Yeah, that's the one. No, that's not the one I want. Battery holder, that's the one I want. Okay. Okay, here you go, a battery holder. We can buy those things in electrical stores. It's a cap. We connect my battery to this cap. Those things are very cheap, okay? Like I said, those are mass manufactured devices. It's just a wire connected, with a connector to conveniently connect your battery. If I touch these wires, this other one, it should see a spark, okay? Don't do that. We don't see a spark in this case, huh? Interesting. Maybe my batteries run out. Let's see if I can get my LED to light up. my positive, yeah, positive, right here. Positive, right in here. Yeah, do you see that? The light turning on, right? Here you go. I'm going to turn it off, okay, and turn it on. Now I can use my LED in a rather safe way. My LED is going to last longer because this battery here is moderating the amount of the current. You don't want a very high current, otherwise you burn your LED quickly. And we can even measure the amount of current that we have here. It's 718 right now. Any questions about that? We're gonna do some more, next time I'm gonna do some exercise on this law. And we're gonna get ready for the final exam on Thursday, okay? So let's take a little break now. And in the next 10 to 15 minutes, I upload the exam for you. Okay, this time, here you go, let me write it down here. This time I will, okay, this time there are two different versions of the exam. Okay, half of the class will get version A, the other half will get version B. Okay, so I will upload, here you go, I will upload both the exam and the spreadsheet to your personal folder. Okay, so you don't have to worry about that. I did everything for you. All you have to do is to open the spreadsheet and start filling up the answers to each question, okay? So I see you in 10 to 15 minutes.
Professor, I have a question.
Yeah.
So I should delete the file I made for the third test? Because I just put one
Yeah.
up there, so I should delete that? Okay, thank you.
Yeah. Mhm.
Oh wait, Professor, so I have I have my Scantron thing that says exam 3. Am I able to can I just keep it like that?
Well, use mine. I'm going to upload that for you. Because, yeah, use mine. Let me upload it right now. Yes, use the one that I provide to you, okay?
Okay.
I'm going to start uploading. I'll upload shortly. Each one of you is going to get both the spreadsheet and the PDF file for the exam.
Okay.
Okay? Here you go. Exam 3. Okay, see exam 3A. I'm going to give you, those two files. Don't forget, put in this format, last name first, first name next. Okay, that's for 3A, the exam A, version A. And that's the exam B.
Oh, do I already have it?
Yeah, I already have. I'm gonna put there in your folder, personal folder. Just make sure you put your last name, first name here. That's the only thing you have to change. Okay? I'll see you shortly.
So we put exam 3B.
No, I already have it here. So I'm gonna tell you who is gonna be A, who is gonna be B. Okay? I haven't decided that yet. Half of the class will be doing exam A. Half of the other half is gonna do exam B, version B.
Wait, Professor, can you repeat that one more time? Exam, we're doing 2 exams?
No, here you go. There are 2 different versions of the exam.
Oh, 2 different versions.
Exam 3A and exam 3B.
Oh, okay.
Half of the class will get version A. I'll choose who will get the version A. The other half will get version B.
Oh, okay.
Okay, I will upload both the exam and the spreadsheet to your folder, to your personal folder.
Okay, thank you.
Okay.